Dear ladies and gentlemen, my name is Astrid Schneidewind. I'm operating a neutron spectrometer at the German neutron source in Garching, nearby to Munich. But today I'm asked as the president of the European Neutron Scattering Association to introduce you into the European neutron landscape. Please let me start with the Users Association, which I represent here, ENSA, to let you know where we come from and how this landscape presentation is provided. ENSA is the representative of the neutron user community. We want to be the voice of the user community when dealing with the research infrastructures on one hand, and on the other side with the political decision makers. At this time, ENSA represents 22 member countries, but there are more countries interested to become an observer or maybe later on a member. We assume to represent about 7,000 neutron users in Europe. And the important point is that we try to act mainly independent, which doesn't exclude the cooperation and exchange with the facilities and politicians. But the independent voice of the user community in our mind is a very important aspect to work within this environment of scientific large-scale infrastructures. In ENSA, each member country is represented by one delegate, and for sure we have an executive board which organizes the continuous work and represents ENSA in politics and for the public. There's a lot of tasks we want to fulfill, but all these things are thought in a way respecting the different needs and constraints and conditions in the national communities, but organizing everything and speaking under the point of view of the European interest of the user community. To go for the landscape discussion, I want to start with the landscape analysis published in 2024 by ESFRI. ESFRI is the European Strategy Forum on Research Infrastructures, a cooperation of a lot of European member states to finance and organize scientific infrastructures which are too large, too complex, or too expensive to be operated by single states. And one part in this landscape analysis is the claim what is needed to make an experiment successful, as mentioned here. And I feel it to be very important that it's not only providing a probe or providing a facility or maybe an infrastructure in other cases, but there are more important points like the provided access of the users to these facilities, which includes travel organization and finances to prepare and to go to the facilities. The experimental support is extremely important, which includes technical, scientific, and analysis levels, such as setups, calibration, and experimental environments, but also the data acquisition, the data management and analysis, including software, metadata, and in our days, for sure, we want to make the data fair. I come back to that at the end. In this landscape analysis, all the analytical facilities are connected in some way. And one important point is that a part of that, for instance, photons and neutrons, cover a very multidisciplinary field to serve users from fundamental science to applied research, coming from material science, biology, or chemistry over physics, health, heritage science, and things like geology and so on. And I want to add to this characterization our experience in ENSA that in addition to single experiments, which are still there, but have been a much larger part in the past. So these single experiments focusing on a very single focused question and lead to reasonable publications. In our days, most of the studies are very complex and trying to come to a deep understanding of either the principles of an effect or the processes like catalysis, which need several experiments on maybe different instruments of one probe, or using complementary different probes, but also very often going to a theoretical modeling and use deeper or advanced data sciences to come to this understanding. And this changes a lot and asks for, on one hand, very experienced and educated scientists. And I invite you, and maybe you are here since you're interested, you can be a part of this extremely complex and exciting kind of experimental science. But on the other hand, it requests a quite important collaboration, and very often we ask for synergies between the different partners in this environment. That's why a network is created between the different directions of these analytical physics infrastructures called ARIA. If we go back to the landscape the SV landscape analysis, then you will see that the number of facilities in the Neutron case is much smaller than in the communities using other probes. Nevertheless, these facilities are connected in the LANS initiative to be represented European-wide. And with this, I come back to landscape and the European Neutron science. Europe has had and still has a world-leading position with more than half of the world's regular experimenters. In the ENSA understanding, we don't speak in that case about a landscape. We think we need to see the Neutron community in a kind of ecosystem, which doesn't contain only the facilities. For sure, we need the neutrons to be provided and the experiments to be performed. There are the experimenters who perform the experiments themselves, but there's a lot of scientists making use of the collected data and waiting for the neutron experiments with all the cycle of proposals, experiments preparation, and data analysis to make finally the scientific outcome of that. Yeah, we think we need to include these scientists making use of the collected data into our ecosystem and respect their interests, their impact, and also the focus of the experimental developments to improve and to sustain our ecosystem. There are some numbers given by LENS in the brochure from 2022. They claim for 5,000 euros from 40 countries, 1,500 collaborating institutes, a lot of companies, and 10 facilities with 150 instruments, and a lot of instrument days and operational days and so on. So what do neutrons provide now? The neutron radiation itself is making use of the neutrons as a probe for scientific use. And the neutrons allow us to study and characterize the properties and the behavior of condensed matter from the atomic to the microscopic scale. So of a large variety of space scales and on time scales ranging from 10 to the minus 12 to 1 second. That's a very, very broad variety of opportunities which is provided by them. We try normally to claim it in a short way to ask where are the atoms and how do they move. These are the questions we can answer with our experiments. And there are some special properties of the neutrons which open special fields for the use of neutrons complementary to other methods. So one is the specific neutron-matter interaction, which finally allows neutrons have no charge. This leads to a high penetration into matter due to no charge interactions, which finally leads to deeper insight into materials, to the opportunity to provide sample environments, and so on. We have the magnetic interaction of neutrons with matter, which gives a cross-section which is similar to the nuclear interaction. So there is a direct access to magnetic information in matter. And neutrons are sensitive to light atoms, in addition to many, many heavy atoms as well, which is particular hydrogen, its isotopes, but also lithium, if you think about batteries. So there's a large field where neutrons allow insight to materials which are difficult to investigate with other probes. And we have neutrons with the energy and wavelengths which is close to those of the excitation and relaxations in matter. So even the approach to interactions and dynamics is easy to be done. So we have a powerful tool here. And before I come to examples, I simply want to let you know how the neutrons are produced, which leads us then to the different facilities. Finally, it's two main methods at the moment. We have the nuclear research reactors, which provide a continuous thermal flux with energies between 1 and 150 millielectron volts. And we have spallation sources, which provide a pulsed beam with a very wide energy range and a very high peak intensity. But if you integrate the flux, then finally you come out normally with lower numbers than reactor sources. So we have different properties of these two kinds of sources, and different experiments benefit or suffer from one or the other property. So we can provide a complementary approach to the different experimental techniques or the different experiments themselves. Unfortunately, we have a significant decrease in the overall supply of the neutrons due to the closure of national reactor sources in this century, which not only impacts the amount of experiments to be performed, but also the education of young researchers and the visibility of neutron science in the countries where the sources are lost, which has a quite strong impact onto the community. And this leads to a joint approach of the overall community and all the scientists in this ecosystem to sustain the capacities and the capabilities on technical side as well on the scientific experiments. I want to add that one of these joint approaches is the development of a new kind of sources, which is called CANs, accelerator-driven neutron sources, or high CANs if they have a very high flux, which possibly could help to overcome the problem of neutron supply in the next decade. Simply to show you these different kinds on pictures. So we have the reactor sources. Neutrons meet a uranium nucleus. You have the interaction. The nucleus splits. You have daughter nuclei and fast neutrons, which need to be moderated on one hand to perform the experiments, on the other hand to allow the next fission process. As to be seen here in the reactor building with experiments directly around the source. But fortunately, neutrons can be guided easily, especially with low energies, and therefore we have experimental halls, as to be seen here, where many other experiments can be positioned to make extensive use of the produced neutrons. The same you can see here for the spallation source. We have a fully different process. We come with fast neutrons to a target nucleus, which is highly excited and then evaporates the neutrons to be used to produce these fast protons. We need an accelerator, which has to be constructed in addition, which makes the overall principle more or less on the same level as reactor sources. Simply to show you these different kinds on pictures. So we have the reactor sources. Neutrons meet a uranium nucleus. You have the interaction. The nucleus splits. You have daughter nuclei and fast neutrons, which need to be moderated on one hand to perform the experiments, on the other hand to allow the next fission process. As to be seen here in the reactor building with experiments directly around the source. But fortunately, neutrons can be guided easily, especially with low energies, and therefore we have experimental halls, as to be seen here, where many other experiments can be positioned to make extensive use of the produced neutrons. The same you can see here for the spallation source. We have a fully different process. We come with fast neutrons to a target nucleus, which is highly excited and then evaporates the neutrons to be used to produce these fast protons. We need an accelerator which has to be constructed in addition, which makes the overall principle more or less on the same level as reactor sources. And again, we have the opportunity to guide neutrons into experimental halls. This is the example from ILL here, and here we have ISIS in UK. Going to the map, you can see here 5 larger sources, which are the ILL as the current flagship in Grenoble, France, the MLZ at Ephraim 2 in Garching in Germany as reactor sources. We have a spallation source ISIS in United Kingdom as a classical spallation source, and a continuous spallation source SynQ in Switzerland. And the 5th one is under construction still, the European spallation source as a European joint approach, under construction now and coming to operation hopefully soon. We have smaller sources in Hungary and in the Czech Republic, and so medium flux sources and smaller sources in Poland, in Vienna, in Austria, in Germany, and in the Netherlands. And you see here all the crosses which show the facilities closed in this century. Compared to the world's map or the global map, we see that there are large sources in US, 2 reactor sources and 1 spallation source, and a smaller one here. We have 3 sources in China, 2 sources in Japan, and 1 in Korea. We have 1 research reactor in Austria, providing global user service. And then we have national sources in addition in Pakistan, in India, in Egypt, and in South Africa. You can see here the peak reactor under construction in Russia, where we thought until 3 years ago that it could be a part of the European ecosystem and serving the European community. In addition to the 3 operating sources in Russia, we will need to see if this idea could come back in any future, depending on all the constraints and circumstances. Simply to let you know that reactor sources are not always far away from civilization. We have here the European flagship, the ILL in Grenoble. That's the reactor source to be seen here as well. ILL provides 37 instruments, mainly diffraction and spectroscopy. A little part is going to large-scale investigations, diffraction and SUNS, small angle scattering, and we have reflectometers and 1 imaging machine. I need to claim that even the reactor, as well as the instruments and the guides, have been upgraded and refurbished in the last years. So we have a quite huge potential still to do science here in the coming future. Endurance and Millennium are the programs for guide and instrument upgrades. The newest reactor source in Europe is the FRM at the Heinz-Meyer-Leibniz Center in Garching, Germany. Here we have 27 instruments under operation, plus 8 instruments which are commissioned now. The suite is a little broader. In addition to the typical instruments, we have element analysis. We have 3 imaging machines at the moment. We serve particle physics, which also has experiments at ILL. And we have a positron source, which serves finally we have a positron source, which finally serves 5 different instruments with the world-leading intensity related to positron provision, and we have a medical application here. For the ISIS spallation source, where you saw the photo already, I'm giving you now a kind of a map to get an understanding how the instruments are organized and how they work in real space. Here we have 36 instruments as well, even with a broader suite. And in addition, we have these chip irradiation instruments, which are heavily used. And ISIS, in addition, provides a muon source with 7 instruments for complementary studies using muons as a probe. The SynQ in Switzerland, in the larger environment of Zurich, provides 17 instruments on this continuous source, including element analysis, isotope production, and an instrument for neutron optics. And even here, the guides are upgraded and allow a better use of the neutrons produced by their source, which is followed and will further followed by instrument upgrades to improve the user service and the scientific opportunities of the center. The ESS, simply to show you that we are now nearby to having beam on target, is the facility here, the target building on the left, and the beam path with the installation for monitors on the right. Here, 15 instruments are under construction just now, and the call for the next bunch of instruments was opened recently. So this will be the upcoming high-end facility for European neutron science very soon. And in addition to this kind of high-end, expensive and advanced sources in Europe, we have a suite of national sources, and that's the reason for the European success in neutron science, that we don't have only the centralized sources where the users need to travel. We traditionally have a suite of national sources with a national community, sometimes focused on different on special techniques or science fields, but spreading out the culture of neutron science all over Europe. And I start with Hungary, providing 18 instruments. 12 are provided for European user programs. We have the Czech reactor in Resch, where 7 instruments are in user program. We have the reactor in Delft, which is a national source, which provides 7 instruments plus positrons for research and education on national level. We have the Mainz reactor, which provides mainly irradiation, but 2 ultra-cold experiment stations for the European user operation. We have the Triga reactor in Vienna, which nationally provides education and research on neutron science and quantum physics. And we have the Maria reactor in Świerk in Poland, which is at the moment a radioisotope production reactor, but 5 diffractometers are under reconstruction finally. And the hope is that Świerk will be sometime a European competence center on neutron diffraction. And with this, I'm back to the ecosystem, which needs more than facilities. So there's this intense cooperation within the community, including the facilities themselves, for educating and training of the young researchers, to sustaining the provision of neutrons, respecting the different needs of the experiments and techniques related to beam time and flux, to sustain the scientific excellence of neutron research, and to maintain the connection to the new scientific developments on one hand, and on the other hand, for sure, we want to serve and fulfill the requests of the society, so-called societal challenges. For sure, we are tax-paid and want to answer all the important questions and adapt to the developing needs related to our profiles. And for sure, we develop the methods and techniques for edge-breaking science at all, respecting the complementary of the neutron science to the other techniques in its full width of this wording. And what can we do with neutrons? You see here, for instance, the example of light elements combined with the high penetration depths. In this study, it was shown that the penetration of water into soil mainly depends on the interaction with the plant roots and its H2O reception, and not only from the properties of the soil. In a complementary study here, it was shown how the plant roots absorb the water and how this can be used for developing drought-resistant crops in future. The light elements are very important for health science. Here we have an example for an experiment showing the molecular interactions and the influence of motions to the viscosity of monoclonal antibodies, which is very important for this for the understanding of these antibodies, which have heavy use in healing the diseases. And on the other hand, we all know that photons can solve overall structures within minutes or seconds, but neutrons can now look to the detailed position of, for instance, an hydrogen, or in this case, an oxygen atom in the oxidase, which is very important for the function of enzymes, or in other cases, functions of genes or antibiotica investigated. In this oxidase case here, we learned that there is no oxygen where it was expected originally, but there are 2 instead of 1 amino acids. So the overall understanding of the function of this special oxidase needs to be rethought and corrected. Going for light elements, here you see the example of a study where the distribution of the lithium and the electrolyte and its concentration and different spatial positions is investigated under cycling of batteries. And with the knowledge of these studies, you can change the production processes and improve the number of improve the properties and increase the number of usable cycles of these batteries here. Penetration into matter, for sure, this is very important for material science. Rolls-Royce is back to neutrons. It's the overall example that you can look inside to the material and correlate defects or special properties in real space positions somewhere inside that material to the overall behavior. Here we have a part of an engine, of a jet engine, investigated to improve the manufacturing process. And on the right-hand side, you see this example from cultural heritage, the investigation of dinosaurs' eggs showed that they laid their eggs in the same way as the birds do nowadays, simply looking into the embryos stored as a fossil. We learned that in one nest there are different stages of the embryos and not all the same. So we can conclude on their behavior. Sample environments I mentioned already. One of the very important usages of neutrons is studying magnetic phenomena. On the right-hand side, you see here this very exciting magnetic structures which are distributed over a large real space region with many spins involved into one magnetic unit cell. This is something which is observed only a few years ago, but now leading to a very big wave, hoping and already learning that this can be used for manipulating devices. So there's some hope to make use of these effects in spintronics. And on the other hand, you have this classical investigation of interactions between different magnetic positions in a crystal lattice. In this case, we have a polar magnet, which is used for multiphoroic uses, which is finally technologically interesting or already used for sensor techniques, as well as for electronic devices and so on. Coming to the end, I hope you got an impression already. Mark Johnson will go into more detail in a later lecture. But one thing is the importance of our data. The other thing is that our data are very valuable. It's a lot of effort and finally also a lot of tax money which goes into these investigations. And very often you can learn later on from your data, or you can search in the data, especially in explanation sources. In time-of-flight data, you can search for other aspects which haven't been the focus of the original study. And this leads to the question, can we either reuse data for further analysis, for new approaches to the analysis? And on the other hand, can we make the data interoperable? I claimed that we sometimes need several experiments and different sources or different techniques. So how can we manage that these data can be, on one hand, easily be combined and used together, and on the other hand, later on, can be reanalyzed? And this is going for the FAIR principles. As many people know, there is a huge initiative in Germany within the so-called National Research Data Infrastructure, and the project related to photons and neutron science is DAPHNE. And here we provide the idea, or we provide tools and services to make the whole data pipeline from the proposal to the publication really fair, and provided data in a fair data and in a curated way to make them reusable and interoperable, which for sure means you need to find access them. And one thing is that we do this for the German facilities at the moment, but due to the overall international interaction, we have some approach to other parts of the communities already, but in a second funding phase, we will extend this international collaboration significantly. On the other hand, we are in the application process for EOSC example nodes or prototype nodes in both the directions. On one hand, from the NFDI part, we are a use case, but on the other hand, there is a thematic node proposed going really for photon and neutron science directly. And with this approach, we hope that we can improve the reuse of our data and the sustainability of our data significantly within the near future already. And claiming that, I want to come to the end. I thank you for your interest and your attention. In case you have questions, you can write me directly as the ENSA president. But for sure, if you have deeper interest in neutrons themselves or on neutron spectroscopy, you are welcome to join us on our instrument. And for both reasons, you have my email address here. Thank you very much, and see you somewhere.